Today we are comparing traditional teacher-centered lessons to constructivist approaches to teaching, where the learners are active in constructing their own knowledge. Here is an example of traditional teaching from the movie Ferris Bueller's Day Off. While watching the clip, pretend you are a student in this economics class and see what information you can retain. Also, take note of the way the lesson is perceived by the students featured in this clip.
In 1930, the Republican-controlled House of Representatives, in an effort to alleviate the effects of the, anyone? The Great Depression, passed the, anyone? A tariff bill, the Hawley-Smoot Tariff Act, which, anyone, raised or lowered? Raised tariffs in an effort to collect more revenue for the federal government. Did it work? Anyone? Anyone know the effects? It did not work, and the United States sank deeper into the Great Depression. Today, we have a similar debate over this. Anyone know what this is, class? Anyone? Anyone? Anyone seen this before? The Laffer curve. Anyone know what this says? It says that at this point on the revenue curve, you will get exactly the same amount of revenue as at this point. This is very controversial. Does anyone know what Vice President Bush called this in 1980? Anyone? Something DOO economics. Voodoo economics.
Now, time for a pop quiz on the lesson you just took part in. See how many of the following questions you can answer correctly. Number 1. In 1930, what bill was created? Number 2. This bill attempted to alleviate the effects of? And number 3. What did Bush call this principle in 1980? Chances are you and the other students in this lesson were unable to confidently answer all of these questions. The traditional lecture style lesson used in this class was not a very effective teaching approach. Traditional teaching is not always effective because it focuses on the teacher rather than the students. The students are passive and have limited opportunities to participate. Students tend to lose focus during the lesson. All students move through the lesson at the same pace. The information is quickly forgotten. Students do not have to do any higher order thinking. And overall, students find this type of lesson boring.
The basic idea of constructivism is that students learn best by constructing new ideas based on a comparison with current and previous knowledge. The positive aspects of constructivism is that when people go out into the world, they interpret things they see and experience by comparing the similarities and differences to ideas they already have. Take the ancient city of Machu Picchu, for example. Imagine if this was an independent research project where you had to determine how on earth could a civilization build itself and build a community on top of such a high altitude and actually build structures that were extremely stable. It's fascinating. The traditional teaching method is mostly an instructor-centered model, which initiates a one-way transfer of information, which encourages memorization, and allows no room for thinking and understanding. Constructivist learning methods, on the other hand, make learning an active process. The student is now automatically bringing their prior knowledge forward and clearing up misconceptions. Students also share their experience with their group and learn from each other, which is extremely important. Instructors benefit from this as well, because more group work allows the instructors to see many aspects of student personalities. For example, their communication skills, their argumentation skills, and their problem-solving skills, and much more. Some examples of constructivism are in the fields of experimentation. If you have individual or group experiments followed by a class discussion, you are encouraging constructivism. Research projects are another example, where students research a topic and present their findings to the class. Third, field trips. Students get to see real-world context for concepts and ideas studied in class. Fourth, films will provide a visual context and another learning experience. The most important aspect of constructivism is having class discussions, because this will enable students to share their ideas and their knowledge with their classmates.
Although constructivism does have benefits in student learning, there are a couple of major criticisms brought against constructivism by Michael R. Matthews from his 1994 paper titled Constructivism in Science Education: Some Epistemological Problems. Matthews notes that the constructivist approach to science is that students try to make sense of the world. Asking students to make sense of scientific concepts is an unstable ground, because many discoveries in science actually defied what was, at the time, considered common sense. There is also the issue that certain scientific phenomena cannot be experienced, so how does one make sense of this? There's also a cultural clash, in that what makes sense to some people might not make sense to others. Matthew's point in all of this is that to discover the truth, appealing to what makes sense is not the best way to get there. For a constructivist approach to work in a science classroom, boundaries need to be applied, in that it cannot be 100% student-centered. Science relies heavily on previously learned materials, so if there's a shaky or poorly built foundation on earlier concepts, learning current concepts will be difficult. A teacher is required to set the boundaries and to keep the students on track, in making sure that if misconceptions do arise, they are dealt with immediately. Constructivism has a place in science, but there must be a fine balance between this approach and the teacher-centered approach. Students need to be the ones making the connections and discovering the aha moments, while teachers need to be more of a guide to their students rather than a stern taskmaster. They can and should help their students where possible, but they should never be the ones doing. The students need to be the ones doing. Those doing are those learning.
Science teachers, we were interested in knowing how cognitive psychology, which constructivism is a branch of, could help teach math and science. We found this example in the Globe and Mail of Dr. Sherry Mantica from Memorial University in Newfoundland. Dr. Mantica created a remedial math course with the help of a colleague, the cognitive psychologist Mr. Darcy Hallett. The course was created because many students entering the university failed the mandatory math test. The collaboration between Dr. Mantica and Mr. Hallett bring forward the facts that successful math learning requires knowledge of the rules as well as automatism of basic skills. Indeed, one cannot learn to do math well by immediately immersing oneself in problem solving, just as one cannot learn to play soccer well by immediately concentrating on playing. The problems encountered at the beginning of university in math come from widespread use of problem-solving learning. 12 math curricula recommends an increased emphasis on problem solving and a decreased emphasis on numeric and symbolic manipulation. In problem solving, students are submerged with too many things to tackle at once. Therefore, the acquisition of new skills can be technically difficult, as it is best to not introduce other demands to the student until specific skills are mastered. By de-emphasizing the manipulation of numbers and symbols, skills are not practiced enough to achieve automaticity, which frees up some brain power for the acquisition of new skills, tackling of new problems. Relevant skills can be improved by practice, the substitution of efficient skills for cumbersome skills, and the use of shortcuts to reduce steps. But none of these are emphasized in modern curricula guided by the curriculum and evaluation standards for school mathematics in Newfoundland. Nevertheless, one simple thing could help improve students' success: practice. And the literature of cognitive psychology heavily supports the importance of practice. Let's look at two examples from the literature. Haverty in 1999 reports that concentrated practice facilitates complex problem solving, and that mathematical discovery is dependent on prior skill level. Skill development usually is a consequence of practice over time and results in both the availability and speedy access to known facts and procedures. Gamble and Zhu report that differential amounts of practice over more than a decade facilitates arithmetic skills, and that early practice in single-digit arithmetic leads to faster access to basic facts. The fact is that by applying principles of cognitive psychology to math, Memorial University helped the students taking the course to increase their graduation rate by 240%. Thank you, Cognitive Psychology.